So welcome everyone. It's nice to see so many people join. So we'll just start in a few minutes time. Yeah. It's nice to see that so many have joined. So maybe in 2 minutes time, maybe Amanuel, you can start by giving us a brief intro about yourself before we get into the paper reading. Yeah.
Yeah, can you hear me?
Yes, I can.
Okay. Thank you so much, everyone, for coming. My name is Amanuel Mersha. I am from Ethiopia, specifically eastern part of Africa. Um, my my thesis. So I finished my master's last July, and my thesis was on how can we develop efficient models that can have that can still achieve high accuracy. In most cases, when we apply this efficiency mechanism onto different models, accuracy somehow drops, right? We can see this with quantization, um, pruning. We always lose accuracy. And one thing that I strongly believe is that the current deep learning models, they are highly inefficient, and I don't think that we're using the parameters that much efficiently. And my work is how do we increase the efficiency while achieving the same or higher performance. That's the whole objective of my research. And this was what I did for my master's thesis. Um, the full paper is still not out because we sent it to a journal, but the early version, um, which appeared in 2022 nearest workshop, is available. The links online. I can share it. Um, but the paper will be out like very soon. Okay, Hanok is here.
Yeah, thanks so much.
Yeah. All right. Sorry
Okay.
for.
Give me a second. I think I should turn the lights on. No, it's better. Okay. Okay.
So
Okay.
maybe, Aman, have you introduced yourself briefly before that?
Yeah.
All right.
Okay. Um, so I think my screen is visible, right?
Yes.
Okay. So let's start with the summary of the whole research. Transformers are impressive. We've seen their applications for many years now, but they are extremely expensive. And the solution that we have is, let's activate some of the important layers given an input and skip the others, the irrelevant layers. And with that, we hope that we can boost the inference speed. And in this case, we increase the efficiency, the speed by 53%. And the accuracy also increased, but not always. It at least achieves us the normal models, but it also increased in some of the models. And we introduced some furthermore improvements. So that's the whole point. And I'm gonna be explaining about the motivation behind this work, this transformer model, the problem statement, solution, the experiments, and the analysis and conclusion. So deep learning, we've seen all these applications. It has been applied to multiple areas. But in 2017, some of you might have, I know some of you might have experience in transformers, but not everyone. So that's why I'm including transformer here. I might be fast, but if you want me to explain more, let me know. Since 2017, transformers have been applied to multiple areas: computer vision, NLP, robotics, drug discovery, game playing, and many more. But they are expensive due to large data need, as well as large number of parameters and the costly matrix operations, specifically called self-attention. And this directly affects increases the carbon emission. There are papers showing, how much deep learning is contributing to carbon emission. It also increases the economic disparity between different regions. Those people who can afford transformers, they can implement really cool applications. But those people who cannot afford these models, they will stay behind. We need to make them efficient. That's the whole point. And if we make them efficient, we would get their merits, and that's what we want after all. So transformers are general purpose deep learning architectures that work by explicitly computing the relationship between parts of the inputs. And unlike recurrent neural nets, they process the whole input at once, and they process images. At least in recurrent neural network, processing images not that much application. I mean, there are some papers that show, but it wasn't that much useful. Unlike CNNs, however, they process sequences, so text, any kind of data. They are able to process graph data, tabular data, any unstructured. As long as we put them in this token format, they can process them. So they are general purpose. How do they work? Whether we have a text or an image, we basically patchify those into vectors, where each patch will have its own vector, and then we basically push them through the self-attention module, which basically computes the relationship between each of these tokens. So in this case, for example, we have the and cats, and what's the relationship between the and cat? And as you can see, we have n squared computation as well as memory requirement. Then after this, the intermediate layer, we have the feed-forward network, and this takes the whole self-attention output and then kind of widens it, I think 4 times in most transformers, and then compress them back to their original hidden size. Finally, we would get a beautiful relationship just like this. So each word will have this relationship attached to it, where the relationship describes the relationship matrix describes how is this particular word related to the others. And in a way, like that's how we also operate. For example, in this case, what is the word it's showing? And in this case, it's focused mainly on animal, the word animal. In this particular case research, we exploited this class token, and let's see what that is. So when you patchify your image inputs, just like here at the bottom, we would have our patches, but we will add one more randomly generated class token initially, and it's called class token. And what happens is, like, after we propagate this inputs multiple times in the forward pass, in the final layer, we take this class token and use it for classification. So it's used for classification, but there are papers that showed this. It basically summarizes what the whole sequence is about. So that's the main idea that will be that is exploited here in this paper. So first, let's see some part of the motivation. So you take similarly parameterized small models and then see different efficiency methods. And in all of them, what you see is, like, this is the baseline, for example, and then accuracy somehow drops when you apply this pruning, skipnet, or quantization, and so on. Accuracy generally drops. Of course, the speed increases, but the accuracy drops somehow. And we would like to change that. So let's go to the intuition. All inputs are propagated through all the layers. That's normal for deep learning. But the question is that necessary? And specific cases, say you have a vision transformer with 12 layers, and you can get 83% accuracy with that. Now, to increase to 87%, you have to double the number of layers, also increase the hidden size. And why? Like, for 4%, for 4 or 3% accuracy, like, you have to double the number of layers. And that's why I say they're extremely inefficient. And here's the question: can we at least skip the next 12 layers for the first 83% of the images that can be correctly classified with the 12 layer? And that's the whole question. And basically, the next 12 layers are kind of unnecessary for the first 83% images. And the trick here is to skip those irrelevant layers. So this is, one is sparse in a way because, like, we're not using all the parameters when we compute an image, but also it's adaptive because it's adaptive to each individual image. So each individual image will have different paths of layers instead of the normal, all layer computation. So the proposed solution is, let's have an RL agent beside the transformer. And so this agent learns to take the class token that I showed you earlier, and then determines if the input should pass through the next layer. So if we are going to activate the next layer, it will output yes or 1. And if not, it will skip. So the output will be 0, and then we will just skip or jump the next layer. So here's the typical network. The orange arrows show the forward pass, and we have our cross entropy loss, the green one here, and then the back propagation would be the green arrow. Now, this is the architecture. On each layer, we have our agent here and our agent here. And depending on the decision by this RL agent, the input might go through the next layer or simply skip it. And we have our cross entropy loss just like before, but the backprop will be on the original path where the image is computed. So this is extremely dynamic. Instead of having a static, path, we have a different, a completely dynamic path. Also, like here, you can see that the RL losses training the agent parallelly with the transformer. So both are trained at the same time. Their gradients are not connected, but they are trained together. The purpose, so here is the RL agent. So specifically when we zoom in into one layer, this orange is the inputs, and then the last part is the class token. And we take that class token and then give it to the agent. The agent will output yes or no. If it's yes, it will go to the blue layer, which is the transformer layer. If not, it will just jump this layer and it will be simply the output. So it's basically identity operation. So when we talk about RL agents, the first thing is the state. So in this case, it's the class token and it's a continuous space. It's embedding. The other thing is the action, and the action here is the skip or the process decisions, discrete actions. Now, as long as the model does not, so here's the kind of the philosophy behind creating this loss function. As long as the model does not underperform, let's reward the RL agent for skipping the layers, the relevant layers. Otherwise, if it underperforms, let's punish it. And hence, our reward would be accuracy, A. The accuracy is, yeah. So the accuracy here, AI is given an image. The accuracy is basically, is the image correctly classified or not? It's not the real accuracy that we typically compute with, the classes. It's just, is it correctly classified or not? That's the whole point. That's the whole thing that we need from here. So that's the accuracy, and the values are either 0 or 1. 0 if not correctly classified, 1 if it's correctly classified. And the layer activation is how many layers were activated. Let's say you have 10 layers, you activated 6, and that would be 6 over 10. That's 0.6. And the range is between 0 and 1 because we were taking the ratio. And so here is the thing. If A is greater than L, L is the layer activation ratio. Great, keep it up. That is, we're having accurate prediction with lesser number of layers. And the ideal case is if we get accuracy 100% with layer activation of 0. That's what we want, right? That's ideal. We're not going to get that, but as long as we minimize the layer activation while increasing the activation, the accuracy, that's good for us. Let's keep it up. If the accuracy is equal to the layer activation ratio, that's the normal vision transformer. So you activate all the layers and you get accurate prediction. That's the normal. What we don't want is if accuracy is less than the layer accuracy is less than the layer activation. That is, the image is not correctly labeled, but we activated some number of layers, and we don't want that. So let's punish in that case. And as you can see, it's multi-objective optimization. And in this case, I just simply subtracted. But one option is to divide the accuracy with layer activation. It didn't work much. I also did not investigate why that much, but we can have different sort of functions here. This one is very simple, very easy to understand. Okay, so the proposed solution schematics looks like this. The RL agents, it's a basic single layer feed forward network. Each agent at each layer are independent, but they are trained together. And each layer is one, each agent is one layer, not that much. So we can increase actually to recurrent neural nets, but one is it will be slow, and um, for some reason, sometimes it generates one same decision for all the agents. So for the layers, we can use one layer or one agent for all the layers. So the problem was it generates the same decision for all the layers, which is not okay. The RNN was better somehow in that case, but it was very slow. But still, like having one layer for each of the agents, the layers was enough. Okay, so what algorithm did we use? Reinforce with baseline. It's the basic, one of the basics, the basic algorithm in reinforcement learning. Now in this case, the reward is made only in the last layer. So here is the reward. Sorry. The accuracy is calculated at the end after we computed everything, and the layer activation also, the layer activation ratios also are computed at the last layer. So we only get reward at the last minute, not in the intermediate layers, and that makes it finite horizon problem. I think P should have been L here. Anyway, our reward is A minus P, and we cannot estimate reward for the earlier layers because we don't have any ground truths, right? So the only way is to propagate back from this last layer reward to the other layers through this discounted reward propagation. So this is basic RL configuration where we just apply this discounted reward, discounted return, and then we calculate our baseline, which is G minus some baseline. I used this for the baseline. I used two layers of feed forward. Then we have this gradient update mechanism, and that's how we calculate here. G minus B, we take the log of the action predicted, and that's how it's basically trained. So the whole point here is like take the basic reinforcement learning formula and then apply it to the efficiency setting. That's it. There is no new formula here. We can even like use some other algorithms like PPL, but I didn't find it that much useful because like some of these algorithms go extra step, cost, incurring more computational cost when we train. This one was the simplest. So I did some tests, and the first was just preliminary test. Then I reproduced the vanilla vision transformer from some other paper by Lee and et al. And we applied this RL agent on their transformer, just test, if we increased the accuracy and increased the efficiency. Also, like we tested whether transfer learning is, possible here. And then we applied some optimization after that using genetic algorithm. So this was the hyperparameter in this case. So I didn't have that much compute at the time. So it was all of these experiments were done on small models. As you can see, the hidden side is 384, layers are 7, 9, 10, 16. Now, this is the performance result. So I didn't link the papers here, but I will do. The ResNet are just there for a reference. Okay, the vision reproduced, you can get like 95% on CFR10, 75.44 on CFR100. The dynamic one, which is our proposed solution, as you can see, is better for all of these data sets. And when we apply transfer learning, so we train CFAR 10 first, and this is easy to achieve, like 95%, and use it as a pre-trained layer for CFAR 100 in Tiny ImageNet. And as you can see, in both cases, dynamic vision transformer from scratch is better than the static one, and the pre-trained one is also better than the static pre-trained one. Now let's see the efficiency. So our focus was not this, actually. The accuracy was not the focus, even though like it's included in the loss function. The important part is like when we maintain the performance, did we increase the efficiency? And this is a small 9-layer model, 1.8 million parameter from Lee's paper. And the way we computed the efficiency is, let's say we give it one image per time, like at time, and per second, how many images can the static vision transformer process per second? It was 207, and the dynamic vision is 250. So it processes 20% more images per second when the batch size is 1. When the batch size is 16, the static vision transformer processes about 3007, but for the dynamic is like 3057. The efficiency here gets lower. So there is this batch size where the skip yes or no, the agent's computation is almost equal to not skipping. So that's where we don't see that much gain here. But as we increase the batch size, let's say 64, it becomes 8%, and for 256 batches, it will be 49%. And as we increase the batch size, the performance, the efficiency gain will be much more higher. This is the same on all the models. In this case, I took the larger one, which is about 9, 12, 14 million parameters. And okay, this one is 10. Sorry, I think this one is a mistake. So 6 million, 9 million, and 14 million parameters. And as you can see, the performance, the speed, or the image per second has increased by 38%, 45%, and 145% for the 16 layer. And this efficiency actually is much bigger for larger with models with large number of layers. This is per GPU per model. I tested it on Colab Pro. I don't know what GPU they use. This is on RTX Titan GPU, and on Colab Pro, like we get 51%, 43%, and this is the last one. So there's one thing, I think on Colab Pro, like they only give you like one thread. This one is multi-threaded. And when you have like even, old GPUs from all time or cheaper GPUs, this method is actually very good for you. When you have the 16 layers, the accuracy gain is much bigger than the expensive GPU. So this method is actually much more better for older and cheaper GPUs. The reason is like when you have 16 or large number of layers, actually you don't need that many layers. And this is what I said earlier, which is they are extremely inefficient. They don't use the parameters efficiently. And there are papers, I think from 2015, that showed that, when you have resonance, the effective number of layers that you need is about 15 or something like that out of 34 layers. and that's because of resonates. Kind of, even though you activate many, you activate all the layers, but they are not necessarily being useful. It's just the idea of resonate. It propagates the layer, the inputs from the bottom of the layers to the upper part. But generally, you don't need that many layers, and in most cases, you only need very small number of layers out of the whole stack. This is on a graph, assuming that the vanilla is 0% in terms of uh, efficiency, like that's the baseline, and over that, like when you use Colab Pro, this is for 7 layers. As you can see, with different batch sizes, you get different. Around 16, somehow that number, the efficiency gets lower. The efficiency difference gets lower. But as you increase the number of batches, generally you get better for cheaper GPUs, and for expensive GPUs, it also increases, but not that much. Same here for 10-layer vision transformer. Again, like on 16, it gets lower. But the good thing is none of them lower beyond below 0. And for 16-layer, as you can see, the difference is much higher. This is because we skip multiple layers. Okay, so in terms of memory efficiency, the model size increases by small fraction because we are adding new reinforcement learning agent. But especially for large models, that's noticeable. That's not noticeable because you're adding just one layer feed for our network, and the input size is like the hidden vector size. So if the transformer has hidden vector of 768, then the memory addition would be 768 because that's the only prime. That's the number of primes that you need. So this is for small models, and then this is for large models. And when it's large model, like the number of parameters added is very small, so it's very close to 0%. Now, on each inference for each image, a new path is going to be computed, right? So why do we get the efficiency? So say you have 9 layers here. Each one of them represent a layer, and 1 shows activation of that particular layer, 0 shows deactivation of that layer. Now, most images, like 52% of the images, are computed with this path. So they only activate the first 5 layers, and they ignore the rest of the layers. So that's where you get the speed gain, okay? And the next 9% of the images activate the first 6 layers and ignore the next 3 layers. And the next 6% activate this path. As you can see, the 6th and the 8th layer are not activated, just the 7th and the 9th only. So as you can see, like they turn, so most of the images don't need most of them, some of the layers. That's how we get the efficiency gain. So to put them in perspective, with vanilla models, like we have good performance, but no efficiency. And there are multiple efficiency methods. They play, around the efficiency side, but their performance is generally lower than the vanilla models. The dynamic vision transformer, like it achieves some sort of efficiency, but also maintains high accuracy. Now, after training, like I did some analysis, and it still can be optimized. So unlike other methods, the proposed solution, our solution, like does not give control on accuracy speed trade-off. The other methods, quantization, pruning, they give you that flexibility. In this case, this accuracy trade-off is hard coded into the loss function, so we're not going to get that flexibility. The other thing is like the threshold value for skipping a layer is set to 0.5. That's the default value. That's a human bias. The other is the unnecessary layer activations. So in this case, even though the model is still efficient, for each of these classes, around 61% of the images activates like one unnecessary layer somehow. And I was curious, and then can we apply some efficiency method to remove these unnecessary activations? And that's where I revert to NSGA. This is genetic algorithm for multi-objective case, and in our case, like we would like to check whether this 0.5 is actually optimal value. We also want to reduce the number of the activated layers and so on. So after applying an non-sorting genetic algorithm at the same time with the reinforcement learning agent, this is what we get. So we can apply this NSGA with RL agent or plain. I didn't include the slides here because time is going. We don't have much time, that's why. Anyway, when we combine the RL and the genetic algorithm, we get about 76% on CFAR10 and 95% on CFAR100 and 95.29 on CFAR10. As you can see, we even increased the accuracy here. And this is what gives me confidence when I say they're inefficient, because as we apply more optimization, we discover that they're not that much efficient. The plain one without the so if we apply the genetic algorithm without information about the reinforcement learning agent, it doesn't do well, but still we get some sort of efficiency. In this case, the number of layers that are so what we do with the NSGA is like we discard some of the layers completely forever. So what happens is out of the 9 layers, it just drops 3 layers. The plain one drops 1 layer. And this is the the Pareto curve for efficiency versus performance when it comes to genetic algorithm. As you can see, when we combine the RL with genetic algorithm, we get a nice curve that's near to the origin. And also, like, we discovered that 0.5 for skipping, by default we use 0.5, but that may not be the perfect number. Sometimes using 0.25, sometimes 0.75 are better. Okay, let me skip this one. The throughput improvements when we applied this genetic algorithm is initially we had 20%, now it becomes 32. We had 1% for 16 batch, now it's 28, and so on. So it improves it much more better. So key finding is that most images do not need all the layers. Static networks are redundant. Efficient skip policy. So there exists policy that enables high accuracy while achieving high performance. The skip threshold value, it's not always 0.5. We should explore multiple values. Limitation, you might need extra memory space, but generally that's minor, as I showed you earlier. Training time, so there is a slight increase in training time and training costs. Transfer learning scenario, it did well on CFAR 100, but not that much on the tiny image. I think it should be explored to generalize, whether transfer learning works or not. Overall, however, it benefits greatly. The benefits are greatly outweigh the drawbacks. Transfer are, to conclude, transformers are very good at solving various AI problems, but they are expensive because of the design. One key point is all the inputs in the data set do not need to pass in all the layers. So let's train an agent that learns to skip relevant layers given the inputs. It achieved a overall, like, averaging over all the GPUs over all the inputs, we get about 50%, 53% speed increase, lesser energy requirements, or uh, faster input processing. Further improvement can be done using genetic algorithm. So thank you so much. If you have any question, I'd be happy to take it.
All right, perfect. Thank you for the presentation. So I'm going to start with my questions, and then you guys can go ahead and type your questions in the chat, or you can, you know, open your mic and then ask. So my first question is like, are there like layers, like for different inputs that are like consistently being skipped? Because maybe like not all the time, maybe for like 95% of the times, are there layers for different inputs that are being consistently skipped?
Yeah. So let me go to a slide. This one. Yeah. So I did this experiment where to compute this. So as you can see here, I think this is the fifth one, six. The seventh layer is almost not activated almost all the time, only in this for the 60% of the images. So I don't think it's activated for even the other images, but as you can see, like for almost 94% of the time, it's not activated from this graph here. And I think that's a nice question because you can ask even more question with that, which is, why is this activated like only for the 60% of the images? And I did some analysis. I did not include the image here, but one thing you could do is like which images are triggering the activation of this layer. And with that, like you can go and analyze this explainability, like why is this activated, and you can see features in the map, okay, this layer is being activated for this set of features. Yeah.
Okay, so that means, so for example, you mentioned the seventh layer, if I'm not mistaken. So that means we can always like skip that layer without involving the RL, and then maybe like we can decrease or like simplify the architecture of it. Can we like do that for the layers that have no impacts?
Yeah. So here's the thing with that. You don't know when, and like statistically we know how many times they are being activated, but we don't exactly know for which of the images they are being activated. So that's where this genetic algorithm comes up. So it learns, when are they activated, when are they being deactivated, and then completely turns them off so that you can increase the accuracy by some amount. But again, like it learns to discard them always. So we don't know because like this is high dimensional, embedding stuff, and we don't understand those numbers, right? But this genetic algorithm knows how to make the right efficient uh, discarding of the layers, if that makes sense. Okay. Anyone else?
So let's give people a few minutes, maybe, to formulate your questions. And until then, I can ask one other question. So I think you tried this on mostly for images, right? So do you think
Yeah.
that this can be applied for like, NLP or like some audio based
Yeah.
models?
So I was to test that. I was on that direction. So compute issue and some other stuff, you know, happened. I did not. But generally, I believe it works. Here's the reason: transformers are generic, like they have been successful in various applications, right? In this case, we're not changing anything other than the skipping mechanism, and this forward propagation, backward propagation, they are generic for all kinds of applications. So this is just by reasoning that I have, enough confidence that I can say, it can be applied to NLP and others. As far as we care, as far as the transformer is concerned, as long as you give it embeddings, like it works on those embeddings, it doesn't differentiate between whether it's image or NLP, and that's the beauty of a transformer.
Someone asked when is the paper being published again? Aman, are you there?
Oh, okay. Sorry, I didn't know I was muted. Okay. All the information is in the original and the early paper, all the formula, everything. The only difference is more analysis on the full paper. I'm hoping it comes out in a month or so. I'll be posting and I'll notify everyone here on Twitter. Yeah.
There
But
is also
the
another question.
Yeah, the code is also on GitHub, and the paper also has all the important information. Okay.
So I've dropped your website. I think they can find the papers there, right?
Yeah, definitely.
All right. So there is other question. So I wanted to know the process you took to choose those hard-coded parameters.
Which parameter?
He didn't specify.
Uh, it's probably these ones, right?
Yeah, probably.
Yeah. So these are from. There is a paper by Lee. Uh, this paper. Yeah. So this paper, the baseline paper, the baseline model is it's adapted from. I think the paper title is Vision Transformer for Small Data Sets. And the model and everything is adopted from that paper.
All right. So I can maybe ask one more question. So I think you tried it on relatively less data sets, right? So you mentioned
Yeah.
the tiny ImageNet. So what impact will it have on the larger ones, like the ImageNet itself, or like the bigger ones?
My prediction is like the impact is even more amplified on this larger models. The reason is like these larger models, they have wider hidden vector, and that will contain more information than the smaller models. So let's say you have one layer transformer. I'm sure you can achieve like 40% or 30% accuracy with that. And if you add one more layer, you can achieve like 60% or something like that. And I tried this. So what happens is like these 60% images do not need more than 3 or 4 layers maximum. So you would get much more better efficiency score on larger models than the smaller ones, because like computing the smaller models is very easy. Like these larger ones, like they need huge amount of um, both memory and CPU um, resources, right? So whenever you like um, reduce the computation by 1 layer, the difference will be much higher than the smaller ones. That is what I believe it would happen. Um, I think I have to work on the larger models. So one thing I should say here is that when I worked on this, as most African researchers, know, uh, having getting a compute or any kind of resource is very hard for us. So I emailed a large number of lots of people after getting the first result, and only Sarah Hooker from Cohere replied, and most of the experiments here were done on her cloud. So I want to thank her officially here. Yeah, she was really helpful. She also mentored me when I um, run the experiments and so on. So lots of help from her. Any more
So
questions?
we have a few minutes. So if there are questions, feel free to jump in.
Hope you can hear me. So
Yeah.
this is more like a general question. Is there anything you're working on apart from this, Amanuel?
Yeah. So at the moment, I'm working on different research areas. But one thing that you can take from this paper is usually we use this reinforcement learning for specific task, right? For let's say stock market analysis or controlling a robot arm or something like that. But we can use it also to control the deep learning components that we have. So it can be like a brain in a brain. So one specific research that I'm working on even this week is on the side is using this RL agent to uh, kind of control the learning rates based on each layer and the time. So usually we set the learning rate by hand, and we have schedulers, to schedule to drop the learning rate as we go in the training. But we don't know if that's optimal, and people come up with new optimizers every now and then. My hope is like this agent will, as we train the model, we'll learn how to set the learning rate by itself. So it will be like auto learning rates. So that's the name actually. Anyway, hopefully, so still this experiment phase. I'm hoping that to write the paper in the next few months. The other major area that I'm working on is, these, as I said, like deep learning architectures are very inefficient. So um, we should come up with new architectures that work in a different way and that are easy to explain and robust. We can where models that we can verify their robustness with numbers. Like we can say this is robust, whatever data set we have, it's this percent robust against this, let's say, out of distribution or any kind of challenge. So I'm working also in those directions. Yeah, those are some of the research areas I'm working on.
Oh,
Awesome.
nice.
Perfect. So maybe one last question. So you used RL much for decision making on which layers to skip. So if we use a different kind of, rewarding mechanism, or like the RL, like a different way, do you think that will impact the overall efficiency of
Yeah,
like your approach?
definitely. So in this case, I used the algorithm is the basic one. The loss function is very basic, like simply subtracting from the accuracy, subtracting the activation ratio from the accuracy. Um, if we so we can, there are multiple ways to explore this. One is like better loss function, better agent structure. For example, I used single layer just to minimize the computation, but for larger models, like it will be the agent will be insignificant when compared to the main network. So we can have slightly complex RL agents. Okay, so th those are those are ways in which we can um, improve this model. Also, like instead of skipping, we can also exit early, and that will minimize the number of decision making. So that will also improve. Um, so yeah, so those are some of the directions that we can take from here.
Perfect. So if there is any last question, we can take one. So if there isn't any questions, so maybe if people want to reach you out, so how can they reach you out? Like, where are you active on?
So I hope you drop the link. You can check my Twitter. You can email me. You can. I think I have my phone number on the website, so you can uh, text me on WhatsApp. So those are possible.
Perfect. Thank you, Amanuel, for presenting your work, and we hope this will not be your last. Thank you
Thank
for
you.
giving us your time.
Uh,
Yeah,
okay. Thank you,
everybody.
everyone, for coming, and thank you for inviting me, and thank you, Sarah, for helping me achieve this. She was really, really helpful. More than I can say.
All
Okay.
right,
Have a
perfect.
good night, everyone.
All right, thank you, everyone. We'll see you in 2 weeks with another guest. Thank you for being with us.